Hello, everyone. My name is Vinayak Kumar, and today I'll be presenting joint work with Venkatesan Guruswami on the pseudobinomiality of the sticky random walk. So I'll first discuss the context of our project, and then I'll introduce the necessary background, and then we'll discuss our main results and proofs, and then finally we'll end off with some recent work that's been done by the community and future directions. All right, so first, our project, our project's context is takes place on the random walks over expanders. So if you don't know what expanders are basically a type of graph that where all the vertices are connected with each other, but they don't use that many edges. And these graphs are very useful in pseudo-randomness. And it basically stems off of the fact that random walks on expanders, they're very good at simulating pure randomness while using a small amount of resources. And so these graphs, they appear in many explicit constructions of various pseudorandom objects. For example, pseudorandom generators, extractors, error correcting codes, or error amplification protocols. And what our project is specifically going to be dealing with is mathematically, what are all the statistical properties of an expander walk that are very pseudo-random, like they're very close to that of a purely random bit string. So just to review what an expander is, they're d-regular graphs, and we think of d as small in terms of the size, or in terms of the number of vertices, because we want it to be sparse. And the combinatorial definition states that any small vertex set, small meaning at most half the number of vertices, expands to a larger one. So by expand, I mean if I add in all the vertices that are adjacent to one of the small set vertices, and I combine them into a bigger set. This bigger set is always some constant scale larger than the small set. So in this example, the green set is our small set, and then when we expand it, we get a blue set that is twice as large. And so if it's always twice as large, no matter what green set I chose, then I can call it an expander with a size 2 like expansion factor. So that's the combinatorial definition. And it turns out there's an equivalent algebraic definition that has to do with the normalized adjacency matrix. So it's simply saying that the normalized adjacency matrix, if we take all of its non-trivial eigenvalues and they're all bounded in magnitude by some constant less than 1, we call it a spectral expander and with some parameter which is equal to that constant bound on the eigenvalues. So clearly the combinatorial definition's more intuitive, but the algebraic definition is easier to work with just because algebra usually has more structure than combinatorics. All right, so in particular, a specific type of expander we're going to look at is one where we mark half of its vertices to be black. And so now when we do a random walk over it, we can analyze the indicator string that indicates whether the ith step was marked or not. So as an example, here's a 6-step random walk that I drew out. And this random walk on this expander that I marked half the nodes on, it creates this following bit string, where I put a 0 on the ith index if that node was white, and then a 1 if that node was black. So I went white, black, black, white, white, black, so 0, 1, 1, 0, 0, 1, like that. So in particular, what we're going to do is we're going to just focus on symmetric properties of the string. What I mean by that is we're just going to look for a random walk. We're just going to look at how many times in the random walk did we visit the marked vertices. And this is equivalent to saying we're only going to look at the Hamming weight of this bit string we generate. So there has been results that study like the Hamming weight of that string, and we can list some important ones. For example, the number of visits is concentrated about n/2 by some expander Chernoff bounds, and this was shown early by Gilman in the 1990s. And then it was also shown that the parity bias was exponentially small, which means the probability that the Hamming weight of the string is even or odd is it's 1/2 plus or minus a very small exponential factor. And this property allowed Tashma to give a construction of almost optimal epsilon balanced codes. So along this similar flavor, we want to look at other statistical properties of this Hamming weight and see how they resemble the binomial distribution. And why the binomial distribution? It's because the Hamming weight of a purely random string follows the binomial distribution. And so this is what we call pseudobinomiality. We want to find the pseudobinomiality of the number of visits, aka how close the distribution of the number of visits is to the binomial distribution. In particular, we take a modest step in this direction by looking at a specific class of marked expanders, which we call the sticky random walk. And so now let us define what the sticky random walk is. The sticky random walk, it has two parameters, n, which is the number of steps, and then lambda, which can be intuitively thought of as the stickiness factor. And it also turns out it's a proxy for the eigenvalue, the expander's second largest eigenvalue. So the sticky walk is going to be a distribution over bit strings. And how it works is it's a two-state Markov chain where the first bit's determined uniformly at random, and then every subsequent bit will stick to the current bit we're on with probability 1 plus lambda over 2, and then with remaining probability, it'll swap to the other bit. And so that's why lambda is called a stickiness factor, because if lambda is equal to 0, if we have no stickiness, we basically stay with probability half and move with probability half. And so this is a purely random string. And then if lambda is equal to 1, this walk is very sticky because after the first step, we essentially stick to that first bit forever, because with probability 1, we'll stay at the initial bit. And so we'll just get 0, 0, 0, 0, 0, or 1, 1, 1, 1, 1, 1. And I'll use a convention that the magnitude of B, a bit string, is equal to its Hamming weight, the number of ones in the bit string. So how do we know that the sticky walk and expander walk are related? So it's been folklore in the community that this is like a walk that resembles the expander walk. And so we make it precise in the following theorem, where we show that the sticky walk is essentially a special case of an expander walk where the expander has second largest eigenvalue lambda. And so in particular, any bound or result we find in the sticky walk cannot be improved in the more general setting of the expander walk. And so this shows that the sticky walk is a necessary proxy towards understanding the general expander. So let's go to our main result here. So here we show a pseudobinomiality result in the form of a total variation distance bound. So note that this is more stronger than established Bayesian bounds. So let S be a sticky walk distribution string, and then let T be a purely random string. So we can basically bound the total variation distance between the distribution of the Hamming weights of these two strings by theta of lambda. And I just wrote it out here, like the Hamming weight, the distribution of the Hamming weight of T is just the binomial distribution, and then this is the distribution of the sticky walk. So something this theorem comes into power when we think of lambda small, because for large lambda, like the total variation distance is bounded by 1, but we basically capture the asymptotic decay of the total variation distance as lambda goes to 0 precisely. All right. So basically the new idea that we use in order to prove this is we essentially do Fourier analysis over this walk, the Hamming weight of this walk, using a special basis, Krawtchouk functions. And this basis is special because it's especially useful for these pseudobinomiality type things. And the reason being is they're orthogonal with respect to inner product that is defined in terms of the binomial distribution, as you see here. And if you work with this basis, you start noticing that the k sub 0 coefficient essentially represents how binomial the distribution is. And then so the remaining terms, the k1 through kn coefficients, they basically measure how much it deviates away from the binomial distribution in a very intuitive and informal sense. And so it turns out you basically just have to upper bound the total in order to bound the total variation distance, you just have to upper bound like the sum of the remaining terms as shown here. And we'll define what G is later, but essentially G will represent like a normalized version of the sticky random walk distribution. So let me now define what the Krawtchouk functions are. The Krawtchouk functions are defined by this expression here. We sum over all bit strings with Hamming weight k of -1 to the alpha dot y for any bit string alpha with Hamming weight L. And it doesn't matter which bit string because this expression is symmetric with respect to alpha. Now we have these inner product relationship that we discussed in the last slide. And from this, you can calculate the norm relationship. So these are orthogonal when r is not equal to s. And then when r is equal to s, you can calculate the norm squared is and choose r. And then from this relationship, you can then calculate what the explicit Fourier coefficients will be simply by using the inner product. And you get this. The k Fourier coefficient is this. So now we're ready to dive into the proof. This is the problem statement restated. And we now rewrite our total variation distance as a binomial expectation. And we get this. And so we basically divided by the binomial distribution and turned this probability into a G of L, which is basically a normalized version of the sticky walk. And our idea now is to Krawtchouk expand G and then upper bound the error terms as we basically hinted towards in previous slides. So first we convert this L1 type sum into an L2 type sum, just because L2 things are usually easier. And now by Parsifals and evaluating the coefficients, the square. So first off, you can verify that the 0th coefficient in the Krawtchouk expansion is indeed going to be canceled out with this 1 here. And so we'll be left with the sum from 1 to n. And then by Parsifals, you get this relationship because we know the norm squared is this. And then now by the definition of the coefficients, you know how we can evaluate these coefficients, we get that this basically equals this expression here. So now we're trying to evaluate this expression. One thing to note is that our binomial expectation is now turned into a sticky walk expectation. And it turns out that evaluating a sticky walk expectation of the Krawtchouk functions is quite nice, and it leads us to exactly find out what these expectations are equal to. And then with that, we can upper bound asymptotically this sum. So this is the precise lemma. For non-negative integers k and s, we basically can calculate exactly what these expectations are. And the proof is it's a cute counting argument in the similar flavor of like balls and urns. And then what we do next is we derive a bound on this L2 type sum that we were working with in the last slide. This should be squared here. This is the TBD, but we're actually working with the squared version. And so for lambda small enough, we can upper bound this to be O of lambda squared. And the proof of this, it's not too interesting. It's just a lot of like arithmetic using generating functions and then approximating expressions. But once we have that, we're done because again, we have this, okay, again, this should be an L1 type norm. And so this L1 norm by Cauchy's utmost is square root of this L2 type expectation. And then by using this lemma, we get O of lambda here. And so that gives our total variation distance result. So there's a second result I want to go over. And this is essentially trying to unify two results. So as we hinted in previous slides, a Chernoff bound was used to show that the Hamming weight of the expander walk is concentrated about n/2. And Toshma used some spectral norm bounding to show the parity bias was exponentially small. So we have Chernoff type arguments and spectral norm type arguments, which are two different arguments. But is there a way to somehow combine these two results? And as a way of trying to quantify what we mean by combining these two results, we show as a modest step, we look at how the majority bit and the parity bit is correlated. So majority bit is basically like, if the Hamming weight's above n/2, it's 1. If it's below n/2, it's 0. And then parity bit, it's 0 if even, 1 if odd. So we do show such an uncorrelation result using Krawtchouk functions again. And this is the precise statement. The probability that the Hamming weight of an n-step sticky walk is even and larger than n/2, it's 1/4 plus some lower order term. And of course, this is the same for even odd or larger and smaller than. And the proof idea is it's a lot of symmetry. And then from the symmetry, you basically the symmetry basically makes everything cancel out with each other, with the exception of like the middle term, which is the probability the Hamming weight is equal to n/2. And so that's why the problem of bounding the central coefficient becomes important. And so we show a bound on this, which is at most O of n to the -1/4. All right, so let's talk about this now. So I've drawn all 4 cases, basically, like of parity and majority into this table here. So our end goal is to show that every single probability here is 1/4, very close to 1/4, 1/4 plus a little O of 1. So let's start off with the top row and bottom row. The top row is all the strings of Hamming weight at least n/2, and the bottom strings with Hamming weight less than n/2. So one can check that if I have a string and then I toggle all of its bits, it's going to have the same probability in the sticky walk distribution. And so that immediately gives us that the top row and bottom row only differ by at most the probability of this middle cases. And then I'm leaving out constant factors because it's not important. And now let's look at the left row and the right row. So the left and right oh, sorry, left column and right column. The left and right columns, it turns out they differ by at most lambda to the n over 2. So it's exponentially small. And this is by direct calculation. In fact, you can, if you write out this difference, it turns out it's actually a special case of the expectation of a Krawtchouk function. And so you can explicitly calculate it to be some constant times lambda to the n over 2. So great. What we know now is that the left row and right row differ by a small amount, and then the top row and bottom row differ by a small amount. But what does that mean? All that means is that the diagonal entries are very close to each other. But that's not enough, right? To deduce that all four boxes have probability 1/4 plus or minus a little. So what we need to show is that the left cell and the right cell are very close. And the left cell and right cell here are very close. If we show that, then we can deduce that all four square entries in the table are very close together. And so to do so, again, it's a symmetric argument here. So we basically look at a map, which we define by toggling a specific bit, a certain bit. And so when we do that, it preserves the probability. This string has the same probability in the sticky walk distribution, and it also toggles the parity of the string. So it's essentially, we're trying to make a bijection between the left cell and the right cell. But it's not exactly a bijection. There's some rogue strings that make it not a bijection. For example, if I had a string that had Hamming weight really close to n over 2, then toggling the bit string might cause it to have Hamming weight less than n over 2. So we have to basically group up all of these rogue cases and then look at the error they make. So it turns out there's only a linear amount of such bad strings, and each of them have really small probability. And so that is irrelevant, essentially. And then, so basically, from all that work, we basically show that this bit flipping map, it shows that the left cell and right cell are very close. And so it turns out the largest error term, since everything was exponentially small, is the bottleneck is just going to be this probability of the Hamming weight of S is equal to n over 2. And so this is where Krawtchouk functions come in. So Krawtchouk functions come in here when we prove that the central coefficient is asymptotically at most n to the negative 1/4. The proof outline is we basically Krawtchouk expand the corresponding characteristic function, where it's 1 if the Hamming weight's n over 2 and 0 otherwise. And so once we Krawtchouk expand that, we can then upper bound the resulting expression we get. And so this gives us our error term, which is little o of 1 in terms of n. And so since this was the bottleneck error term, it follows our 1/4 plus little o of 1 thing follows, because all four entries in the table are exactly the same. So there's been some exciting recent work by Cohen, Perry, and Tashma, and in their paper titled Expander Random Walks, a Fourier Analytic Approach. And some of the cool results they derive is a total relation distance bound for a general expander walk, not just a sticky random walk. And so in our paper, we showed an O of lambda bound on the sticky random walk. So they show an O of lambda times log to the 3/2 of 1 over lambda, or an O tilde of lambda bound on the general expander setting. And so the approach they use is quite similar. In spirit, what they do is instead of calculating the Hamming weight of the sticky walk and the expectation of that, they carefully compute the expectation of the Krawtchouk function on the expander bit string Hamming weight. And so there's a natural question that arises is, can we remove this log factor in order to get this O of lambda bound for the general expander walk too? And another thing they improved upon is a upper bound on the central coefficient of the Hamming weight for expander walks. So if you recall, we showed an n to the negative 1/4 bound. Using some careful analysis, they were able to show an n to the negative 1/2 bound for this function. So there's some future directions that are yet to be resolved. For example, as I said in the last slide, can we establish an O of lambda bound for the general expander walk? Also, can Krawtchouk and Fourier analysis unify the parity and majority results for the expander walk? Because right now we've basically shown a correlation result, but it really depended a lot on the symmetric properties of the sticky walk, and so that's why the bound of n to the negative 1/2 shown here could not be really extended to show a uncorrelation result. So is there a way, rather than symmetry and using maybe some Krawtchouk or Fourier analysis, to show such an uncorrelation result? And then another interesting question is there a way we can reduce the general expander setting in some ways to the sticky walk setting? So for example, there are moment generating function results by Kahale and Rao-Ragev that show that the expander walk Hamming weight, MGF, is upper bounded by a certain case of like a bit general version of the sticky random walk. And so this allows us to lift bounds on monotone symmetric functions from the sticky walk to the expander walk. So is there some result we can show that can lift bounds for non-monotone functions like parity? And so that's another question. So is there a more general class of events that we can sort of lift from a simpler sticky walk to a general expander walk? And so that's all I have for this talk. Thank you for listening, and